Equations you need to know. So you have about 15 equations you are going to need to know. And they're right here. These are the popular ones in CSEC. They have the meanings over here. I have them here, so 11 of them. We have EH, heat loss or gain, units used, joules. EP, potential energy, units used is joules. EK, kinetic energy, units used, joules. P is power, units used watts or joules per second. M is mass, units used is kilograms. G is gravity, units used is newtons per kilograms or meters per second squared. Common letter V is velocity, meters per second. Common letter T is time, which is units of seconds. Capital letter V is voltage. So capital T is temperature. Oh, so capital letter V, voltage, units volts. Capital letter T, temperature. You have units of kelvins or degrees Celsius. And then we have the specific heat capacity, which is joules per kilogram per degree Celsius or joules per kilogram per Kelvin. And so these 15 relationships, right? When you have a question, what I always tell people to do is to write out your variables, and then once you write out the variables, you would know or have some idea of which relationship to use. And you can see that going through the papers or the questions with me, right? So EH is equal to MCAT. EH is also equal to EP. If EP is equal to MGH, we could substitute that in, and we have EH is equal to MGH. We have EH is equal to EK. So if EK is equal to a half MV squared, then if you substitute those values for EK, you will see that EH is equal to a half MV squared as well. EH is equal to power times time. Hence, power times time could be equal to MCAT. So we see that up here for question 1, that EH is MCAT. So we could put that in. And if we want to find power, given the mass, the specific heat capacity, and the change in temperature, we could divide it by time and we could get the power. EH is equal to mass times latent heat of vaporization. And, oh, I don't even have that there. I don't have that there. EH is also equal to M, mass times latent heat of fusion. So if EH is equal to power times time, then PT will be equal to MLV, which is mass times latent heat of vaporization, and PT would also be equal to MLF, which is mass times latent heat of fusion. Now, if this is the thing now, this is another substitution. So this is how it gets wild. That's why it gets wild, you know. If P is equal to IV, then EH will be equal to PT. And if that is the case, it is equivalent to EH is equal to IVT. And then maybe, you know, you could have MCAT is equal to IVT. So you realize you're just substituting. Hence, if PT is equal to MCAT, we could get IVT is equal to MCAT. That's just what I said just now. And if PT is equal to MLV, then IVT, remember IV is indicative of P. That's what P is equal to. So IV, we're substituting P with IV times T will be equal to mass times latent heat of vaporization. And the same case, if you have PT equal to MLF, then IVT is equal to MLF. So once you know these things and once you realize the relationship, you could actually apply your knowledge across the board once you have your variables and everything. But of course, you have to answer a lot of questions, which is what we're going to be doing right now. So see you on the flip side. Welcome to Thermal Physics and Gas Laws past paper questions. Let's get started. Alright, so we have here a question that says, complete table to distinguish between solids, liquids, and gases using the terms definite or fixed, vibrate, move freely, very weak or negligibly weak, and then with no fixed shape. Okay? So we have to So for a solid, we know the shape will be definite or fixed, and the movement of particles or the movement of the molecules would vibrate. Okay. Then for liquids, we know the volume would be definite or fixed, and then the intermolecular forces will be very weak or negligibly weak. Then for gases, we have no fixed shape, and the molecules, the movement will be moving freely, and the intermolecular forces will be very weak or negligibly weak. Okay. Then 2B says students in a fifth form physics class use the apparatus in figure 3A and 3B in an experiment to find the specific latent heat of vaporization of water LV. Figure 3A shows the initial readings as the water begins to boil, and figure 3B shows readings taken after 5 minutes and 45 seconds. And so we have to observe the drawings, okay? So we see here that we have a startup time of 0. We start at 0 minutes, and we have a mass of 375 grams with the water. Then we see the end time is 5 minutes 45 seconds, and we have less water than before. So we have to be very careful when we are looking at our drawings. So this is like observation, and we're going to now report or record what we've seen. So it says, convert the time recorded in figure 3B to seconds. So if you know that 1 minute is made up of 60 seconds, then all you have to do is to relate 5 minutes to X. You say, oh, if 1 minute is 60 seconds, how much would 5 minutes? It would definitely be more. So we multiply 5 minutes by 60 to get 300 seconds. Then we just add the 45 seconds, and we have 345 seconds. So that's the time in seconds overall. Then it says calculate the mass of water evaporated in the experiment. So we subtract the 360 from the 375. So we subtract the after the final from the before to get the mass of the water that's evaporated, which is 15 grams. All right, then the next question was the power of the electric heater used in the experiment was 100 watts. Assuming no heat was lost to the surroundings, calculate the specific latent heat of vaporization of water. So we have power, which is 100 joules per second. We're looking for LV. We have the mass, and we have time. So therefore, we could incorporate PT equal to MLV, and we solve for LV, where we have LV is equal to PT over M. Hence, if we substitute now, we put in 100 times 345 over 15, we get LV is equal to 2300 joules per gram. Okay? And this would have given us 50 marks. This was a 2018 paper, January. Okay, so let's look at January 2019 now. And we have another thermal physics question. It says, explain what is meant by the term the specific latent heat of vaporization of water. Well, the specific latent heat of vaporization of water is the heat energy needed to change unit mass, usually 1 kilogram, of the substance from liquid to gas without a change of temperature. So latent heat is actually referred to as hidden heat. During this time, temperature does not change. Okay? Now calculate the heat energy required to convert 8 kilograms of water to 100 degrees Celsius at 100 degrees Celsius to steam at 100 degrees Celsius. So this is another thing about latent heat. Latent heat occurs wherever there is a phase change. So whenever there is a phase change, there will be no change in temperature. No change in temperature at all. Okay? So as you can see here, we're going from water at 100 degrees Celsius to steam at 100 degrees Celsius. So there is no temperature change. And so we can say EH is equal to MLV. We already have the mass, and we were given the latent heat of vaporization, the specific latent heat of vaporization, which is 2,300,000 joules per kilograms. So we simply multiply these two together to get 18,400,000, and I I just made it a small number, 18,400 kilojoules. Okay, so that was pretty simple enough. Just remember, when you're dealing with latent heat, there's no temperature change, there's only a phase change. Then it says here, define the pressure law. For a fixed mass of gas at constant volume, the pressure is directly proportional to its absolute temperature. So note well, you don't see volume in this equation here. That means volume is constant. So here's another calculation. It says the initial pressure of a sample of gas is 3 pascals. The final pressure is 9 pascals, while its volume remains unchanged. So that means we are dealing with constant volume. If the initial temperature of the gas was 27 degrees Celsius, calculate the final temperature of the gas. Okie dokes. So we have a before and an after. And we're going to just separate our stuff out from in the before, which was 3 pascals and 27 degrees Celsius. And the after is 9 pascals. And we need to find out the temperature change, right? We need to find out, the after, the temperature after, okay, or the final temperature. So remember, whenever you're dealing with gas laws in particular, you have to convert your temperature from degrees Celsius to Kelvin. And to do that, you add 273. And once you do that, you get, you just add it and you get 300 K. And then now we're going to just substitute our values into these equations. And what I did first was solve for T. I made T2 the subject of the formula, where you see T2 is equal to P2 times T1 over P1. And then so we substitute now 9PA times 300K over 3PA, and we get 900K. So as expected, the temperature would have risen when the pressure rose. Yeah. Okay, so let's do another question. This is a 2018 paper. It says, define each of the following terms. Specific heat capacity. So specific heat capacity of a substance is the heat needed to change unit mass of the substance by unit temperature. You could say it's the specific heat capacity of a substance is the heat needed to change 1 kilogram of the substance by, no, not to change, but to heat up 1 kilogram of the substance by 1 degree Celsius. Yeah, so you might see that. All right, specific. So let's do heat capacity. It says heat capacity is of a body is the heat needed to change a body by unit temperature. It is a property of a body. Then it says here, write the formula to show the relationship between the specific heat capacity, which is small c, and the heat capacity, which is big C of a body. And that is it there. Is big C equal to, or capital C equal to mass times common C. In other words, as heat capacity equal to mass times specific heat capacity. All right, so define the term heat capacity. Heat capacity of a body is the amount of heat needed to raise the temperature of the substance by 1 degree Celsius. So it's not specific, so it's just whatever substance or whatever mass, you're trying to raise it by 1 degree Celsius. Okay, so there's a difference. Specific heat capacity deals with real specific units, like it's 1 kilogram, you're trying to raise that 1 kilogram of substance by 1 degree Celsius, whereas heat capacity is the entire body. So if you're trying to heat up, it doesn't have to be 1 kilogram, it could be 500 grams, right? So you're trying to raise the 500 grams by 1 degree Celsius, okay? So that's the difference between the two. All right, so define the term specific latent heat of vaporization. The specific latent heat of vaporization, LV, of a substance is the heat energy needed to change unit mass of the substance from liquid to gas without a change of temperature. Key. So here we see it says a substance which has a freezing point of 80 degrees Celsius was cooled from 90 degrees Celsius to a total solid at its freezing point. Sketch a graph on figure 4 to represent the statement above. So we start here really hot, and by 80 degrees Celsius it starts to plateau because you have that latent heat of fusion coming into play, right? So it's fusing together to form the solid. So you can have this plateau for over a certain amount of time, and that will be it. So just note that here will be this is called a cooling curve, by the way, which is incomplete. And so here will be where the liquid phase exists, right here. Until you come to this plateau here, we have the liquid and the solid phase. Okay? And so by the time you get this next dip here where it's supposed to come down, you're going to have the solid phase only. Okay? So the freezing point is where you have the plateau, always. Now it says, a student conducted an experiment in which 1.5 kilograms of water at 30 degrees Celsius was converted to steam at 100 degrees Celsius. So it says, assuming no heat is lost to the surroundings, calculate the amount of energy needed to heat the water from 30 degrees Celsius to 100 degrees Celsius. So what I like about this question is that they break it up in parts for you. They do. So they start off with going from 30 degrees Celsius to 100. So you're going to have warm water to really hot water. Okay? So because you look at this, you see it's just a temperature change. The phase is the same. So we use the equation EH equal to MCAT, right? Because there's a temperature change. There is no phase change. You write down all the variables that you have, and the variables for the constants, like the specific heat capacities, are usually given at the bottom. Okay, so don't forget that. Note well that the units for specific heat capacity you have per Kelvin. You could interchange that without converting to kelvins or degrees Celsius. You can interchange it, right? And this one had a little mistake, so I put the G in there. All right. Once you write your values, okay, and you solve, you change in temperature, 30 to 100. And note well, when you're doing change in temperature, you always subtract the cooler from the warmer temperatures, right? Just make your life easier. So when you do that calculation, you get 1.5 times 4200 times 70, and you get 441,000 joules. Then the next step was to go from 100 degrees water, or water at 100 degrees to steam at 100 degrees. And as you can see, the temperature didn't change, but the phase did, because it went from hot water to steam. So you would use, whenever there is no temperature change, you would use either EH equal to MLF or MLV, depending on what transition is occurring. We're going from water to gas, so it's going to be LV. And so what we're going to do is mass is equal to 1.5 kilograms. LV is 2.3 times 10 to the 6 joules per kilograms. So you just multiply the M and the LV, and you get 3,450,000 joules. All right. So now that you've calculated the steps separately, they say the heat the water from 30 degrees Celsius to steam so they want the total amount of energy, heat energy that's given off. That's where you add them together, and you get 3,891,000 joules. Okay, and that will be your answer for that one. All right, so here's another question. If you notice, all these questions start at question 4. So this is where they start off most of them, because this one wasn't question 4, but most of them, it's like a trend, so you should be aware of that. So it says, a young student has just entered secondary school. He was accustomed to having his home cooked meals warmed up at lunchtime in the microwave oven at his primary school. He misses this and suggests to his parents that they buy him a vacuum flask similar to the one shown below. So we have a vacuum flask. We have the parts of it being labeled, where we have the cork, the double-walled glass vessel with silvered walls. You have the vacuum area where there's no air at all. And then you have something surrounding the flask, and then cork supports. Using the information in figure 5, it says explain in terms of the principles of thermal energy transfer how each of the following sections of the vacuum flask helps to keep the home cooked meal warm. So they want you to now explore heat transfer. So we know that there are three ways that heat is transferred or can be transferred. We know it's conduction, convection, and radiation. Of the three, only two require matter, and there's conduction and convection. Radiation can actually travel through a vacuum. So once you understand those three types of transfer, you could answer this question really well. So the cork stopper, we're going to note that the cork stopper is an insulator. Therefore, it will trap the heat in within the vacuum flask because it is a poor conductor of heat. Then for the vacuum, a vacuum doesn't contain any matter. Therefore, conduction and convection of heat will be minimized greatly since both types of heat transfer require matter to take place. Owing to this, heat stays within the vacuum flask. Then the double-walled glass vessel with silvered walls. So it's the radiation is minimized as it is reflected back into the flask, and we know that glass is a very poor conductor of heat, so you could actually add that, and this would have given you your 6 marks. Then down below we have a little working out. It says, in an experiment to determine the specific latent heat of fusion of ice shown in figure 6, the following results were obtained. The initial mass of the water is 120 grams. The initial temperature of the water is 35 degrees Celsius. And the initial temperature of the ice is 0 degrees Celsius. So the final mass of the water is 140 grams. And the final temperature of the water plus the melted ice is 18 degrees Celsius. So let's see here. It says, assume the container has negligible heat capacity and that there is no heat transfer with the surroundings during the experiment. So it says, determine the mass of the melted ice. The mass of the melted ice would be the final mass of the water, subtract the initial mass of the water, and we get 20 grams. Then it says, calculate the heat lost by the water. So I wrote down everything that the water was. I know the water had a mass of 120 grams. And then it had a temperature change of 17 degrees Celsius. So it started out at 35, and then the final temperature was 18 degrees Celsius, right? As I said, the ice melted, so heat from the water went into the ice, right, or caused the ice to melt. And so we have all our variables, and we have our known 4.2 joules per gram degree Celsius. And so to work this out now, it's EH, the heat lost by the water, will equal to the mass of the water times 4.2 times 17, I get 8,560 joules. So then over here it says write an expression for the total heat gained by the ice in melting and the melted ice in warming to 18 degrees Celsius. And so we know that heat lost by water, that should be heat lost by water, is equal to heat gained by ice, right? And so that would be 8,568 joules. Now it says, hence, calculate the specific heat, latent heat of fusion of ice. So we could relate the heat that the ice gained to mass times latent heat of fusion, and then we just transpose and we get 428.4 joules per gram. Here's another one. It says some students were asked to carry out an experiment to determine the specific heat capacity of a metal. They used the apparatus shown in figure 5. So they listed out everything, the mass of the metal block, which is 5 kilograms. They tell us that The switch was closed for a time interval of 900 seconds. The change in temperature is 50 degrees Celsius. The ammeter reading was 8.5 amps, and the voltmeter is 12 volts. Okay, given all of that, I still went and wrote it out underneath my question. I said the assumptions made, or the acts. I said using the data on page 14, calculate the specific heat capacity of the metal, stating any assumptions made, and the assumptions made may be that no heat was lost to the surroundings. I was minimized greatly. So we had the time, we have the mass, we have the change in temperature, we have the current, and we have the voltage. So we could write an equation that relates all of these together. We have PT equals to MCAT. And remember that P is equal to I times V. So if we stick it in there, we now have a variable for I, one for V, and one for T. Then we have the MCAT on the right hand side. But we need to make the subject of the formula C, because that's what we're looking for. So C will be equal to IVT over M delta T. You stick in your numbers right there, and you should get 367.2 joules per kilogram degree Celsius. Alright, here is another question. This is dealing with the gas laws, and it says state the equation for the general gas law. That's P1V1 over T1 equal P2V2 over T2. Now it says a little girl blew up a balloon during a Christmas celebration. Explain in terms of the kinetic theory how pressure is exerted by the air in the balloon. So the molecules of mass m of a gas bombard each other and the walls of their container, which in this case is the balloon. As they rebound in a short time t, their velocity changes from initial velocity to final velocity, and the impact force is F in accordance with Newton's second law of motion. F equals to m times the difference in final minus initial divided by time. This force creates a pressure P on the area A of the walls, P equal to force over area. At higher temperatures, molecules translate at higher velocities, and therefore the rate of change in momentum, the force on collision, is greater. The pressure therefore increases. Hence, the more air the little girl puts into the balloon, the greater the concentration of air particles within the balloon. This will cause more collisions with the gas particles within the balloon and upon the balloon's inner walls. These collisions will keep the ball inflated. Okay, now for B, it says a block of ice of mass 200 grams was heated from 0 degrees Celsius to steam at 100 degrees Celsius. Calculate the energy used in joules. So we're going from ice to form icy water, right? So there's a change in phase, but no change in temperature. Now you have a change in temperature and no change in phase, right? So you will see the equations correspond with what's going on. For instance, we know this is latent heat of fusion when the temperatures are the same, so we use EH equal MLV. And when the temperatures change, now when they're different from one point to the next, we use MCAT. Now look at this one. The temperatures are the same here. It's EH equal MLV. So what we have to do now, since we have our little arrows, each arrow represent a change of heat loss or either heat gain. In this case, heat loss. So we're working out each section. We need to convert the 2,000 grams to centimeters by dividing by 2 kilograms by dividing by 1,000. And so once we did the calculations, we get 660,000 joules, we get 840,000 joules, and we get 4,500,000 joules. You add all of that to determine the amount of energy lost in the system. Okay? So that's what you do. You add them up, add up the answers. And we get 6 million joules, or 6,000 kilojoules. Now, If the activity in B1 took place in 6,000 seconds, how much power will be utilized? Now, we're going to have to divide the total amount of heat loss by the temperature. As you can see here, PT is equal to EH total. So you divide 6 million joules by 6,000 seconds to get 1,000 joules per second. And look, you have all the constants here at your disposal. Alright, so it says here determine or define the term specific heat capacity of an object. Now the specific heat capacity of an object is the amount of heat needed to raise 1 kilogram of mass by 1 degree Celsius. Then it says table 3 needs to be completed by inserting the correct symbol and SI unit which relate to the quantity shown in column 1. So all you have to do is put in the SI unit, and for heat capacity is joules per kilograms, and for specific latent heat is LV. Now write the formula for the general gas law, stating clearly what each letter represents. Wow, so this is like what, the second or third time to ask this question. And so with P1 V1 over T1 equal P2 V2 over T2. P1 represents initial pressure, V1 initial value, T1 initial temperature in kelvins. Here we have pressure again. This is P2 final pressure, V2 final pressure, T1. It should be T2 final pressure, not T1 in kelvins. Now, a physicist converts 8 kilograms of water at 33 degrees Celsius to steam at 100 degrees Celsius. Assuming there is no heat loss, calculate the energy required. And what I like to do is do these little drawings so it keeps me on track. And I see we went from 33 degrees to 100 degrees Celsius, and that was it. They didn't say that it went to steam, so we know we stop right there. So there's no latent heat. However, there is heat lost, right, with temperature change. So EH is equal to MCAT. You substitute all values given. So you have E 8 kilograms. You have 4,200, and that is often given. Do you see it? Oh yeah, see it over here. It's given, and then you have to change the change in temperature by subtracting 33 from 100, as you can see here. You end up with 2,251,200 joules. Now it says to convert the water to steam. So now we're cooking on gas. This is dealing with latent heat of vaporization. So it would multiply 8 kilograms. Sorry, the specific latent heat of vaporization. So it will multiply that of water, and you get 80,400,000 joules. When you're done, they're going to ask you, well, how much heat really came off the system? That is where you're going to add the two calculations that you just did, and then you're going to change it to megajoules because that was the request in the question. Change to megajoules, and so you see my ratio set up here, where 1 megajoule is equal to 10 to the 6 joules. So therefore we're going to divide 20 million plus by a million. Okay, and this question would have given you 15 marks. Okay, so now it says stating words the quantity each symbol represents in the equation EH equal to MC delta T. State the SI unit of each quantity as well. So we have heat loss again, that's in joules, that's heat energy. Specific heat capacity is joules per kilogram per Kelvin. Temperature is in Kelvin, so remember they ask you to write it how? In SI units. Okay? So be careful. So whenever they're asking you to write in SI unit when you're dealing with temperature, you have to write it in kelvins. Same here, you can't go put down degrees Celsius because they ask for SI units. Okay? What does the symbol L in the equation EH equal ml represent? Latent heat or hidden heat. That's what it means. Okay, so it says, in an experiment to determine the specific latent heat of fusion of ice using a container with negligible heat capacity, a student obtained the following data. Initial temperature of water, 30. Final temperature of water plus melted ice is 20 degrees Celsius. Initial mass of water is 100 and the final mass is 110. And that's because they added the ice. So it says calculate the heat lost by the water. So we have here, we need to make sure we understand this. So the water is going to lose heat when it's heated, when it cools down from 30 degrees to 20. Okay? You do the calculation here, you get 4,200 joules. Now, it says calculate the heat gained by the ice, the melted ice. Well, the heat lost by the water will be the heat gained by the ice, so it can be the same thing, 4,200 joules. Then now it says, assuming the heat lost by the water is equal to the heat gained by the ice, they kind of give the answer here, by the way. Calculate the specific latent heat of fusion of ice. So you have the markup up here. So now you know that if 4,200 joules is equal to mLV, right? Then you need to find the mass of the ice, and from there you get 420 joules per gram. Okay? So whenever you're dealing with latent heat of fusion, there is no, or latent heat of vaporization, there is no temperature change, none whatsoever. Okay, here we have a graph. It says the graph deals with temperature as well. It says a Form 4 class was given a student or school-based SBA activity on the change of phase of a substance while it is cooling. A Form 4 class was given a school-based assessment activity on the change of phase of a substance while it is cooling. The class presented the results shown in Table 1. So it says plot on page 3 a graph of temperature against time. Both axis may be begun at the origin, and you want to insert the letters A, B, C, D on the graph. Now using a dotted line, so I plotted it, and I did 10 for 2. Every 2 units I put 10 on the y-axis, and every 2 units I put 5. So I could get a nice big broad graph. And we see here that we're plotting, it's nice, and then we have this plateau here. The plateau is indicative of the melting point, also known as the freezing point, right? And we get 70. So it says, in what state is the substance as it moves through B and C? So what's the state of B and C? So the state of B and C would be solids and liquids. It would be a mixture of both. That's why we have the plateau, right? And it says explain the difference. I explain the temperature. Explain why the temperature was constant between BC. They were constant because bonds were being broken, hence the heat appears to be hidden. Okay? As you can see, the freezing point is 70 degrees Celsius. Make sure you label your graph, put the appropriate units, and you're good to go. And make sure you draw your lines going across here. Don't leave them blank. I just couldn't do it. I didn't feel like doing it, but it's understood. Okay, so these are the final questions. It says, state the phase of the solid at C. State the phase of the substance at C, and that will be solid. So by the time you get to C, it's totally solidified. So that would be a solid. Then it says describe what is happening in the solution or to the solution from C to D. From C to D, the substance will be hardening. It will be going through solidification. So just imagine wax being melted at some point. You can really, you could snap it, but not without force. So this question was exactly like all that it would have done, but there is no help. They expect you to calculate whatever they wanted to calculate by doing it in one go, whereas we would have had it spaced out for some questions. So what I did, we went from 90 degrees. I followed the graph. From 90 degrees, it started to melt for at 70 degrees Celsius, and then you maintain the plateau of at 70 degrees Celsius. So you went from solid, you went from liquid in liquid state to solid state. So you see the phase change but not the temperature, and then now the phase stays the same and the temperature changes. So this one, I followed the graph. I looked at the graph and came up with my little drawing right here, right? Just remember, if you have latent heat, you'll always be going from one phase to the next. Okay? I converted the mass to 0.015 kilograms, as you can see here. And we end up with, here the first EH was 528.9. The second EH was 3,225 joules. And the third EH was 330 times 0.56 joules. Okay, so just look at it carefully. And we have here we have here the total amount of energy given off, and we add all of them up. 1, 2, 3, we end up with 4,084.46 joules. Okay, and they gave us all our constants down here, right? Nice. So you have to be careful again, because in this case it's a substance, so the heat capacity of the substance is 1,763, and the latent heat of fusion is 215,000, right? So you have to be careful. All right, so now, and here's another tip. You don't ever need, untip that. So, okay, so it says here, table 2 needs to be completed with the symbols and SI units for the physical quantities. So it's going to be a capital C for specific, for heat capacity, and the unit will be joules per Kelvin, and then specific latent heat of vaporization will be LV, and will be joules per kilogram. Now, question 3 says, state the equation for the general gas law for ideal gas. You know, it's funny, this question was repeated 4 times already, or 3 times already. This might be the 4th. So you can't forget it. P1 V1 over T1 equal to P2 V2 over T2. It says state the meaning of each symbol stated in the equation. Well, anything with a 1 would be initial whatever. So initial pressure, initial volume, initial temperature in kelvins. And then 2 will be final pressure, final volume, final temperature in kelvins. And then here it comes, it says a car tire is pumped to a pressure of 2 times 5 pascals in the morning when the temperature is 23 degrees Celsius, right? So we're going to label this P1, and this will be T1. Now later in the day, the temperature rises to 34 degrees Celsius. So you notice that will be your temperature 2. And from the get-go, you convert your degrees Celsius to kelvins. So we're definitely looking for pressure because volume is kept constant. Volume is kept constant. So we're looking for pressure, the final pressure. So how is this related? P1 over T1 equal to P2 over T2. We transpose for P2, and we end up getting 207,432. All right, so using the kinetic theory of matter, explain why the increase in pressure occurred. Well, at higher temperatures, molecules translate at higher velocities, and therefore the rate of change in momentum, the force, on collision is greater, therefore pressure increases. Alright, so it says now, they're trying to confuse it. It says calculate the ratio of new volume to old volume for the tire if the pressure is held constant while the temperature rises from 23 degrees Celsius to 34 degrees Celsius. So this is definitely going to be our T1, this is going to be our T2. And it says if P is constant, we're going to use Charles's law. And we see here that V1 over T1 equal to V2 over T2, where T2 over T1 is equal to V2 over T1. Hence, if we stick in all the information that we gathered up or conjured up from this previous question, B1, right? You'll be able to answer the question, and then we see that V2 over V1, the value will be 1.4. Alright, this is the end. Best wishes, students. I hope these questions helped you. Feel free to pause. I'm on the brink of tiredness right now. So this is just to help you, especially for those people who are doing in-school internal examination. You could use these questions, these past paper questions, to help you get where you need to get to, right? So, never fear. Make sure you use these questions to help you. And best wishes again. Bye.